Hi, thank you for joining me. I am going to introduce now mathematically the link between free energy and K. When my students ask me what thermodynamically favorable means, we used to say spontaneous in the old days, but that kind of gives you an indication of a rate, whereas free energy has nothing to do with rate. Thermodynamically favorable, even though it is a mouthful, is, I think, got much more explanatory power to it. So they'll ask me, what does that mean? Because it does sound a little vague. And I usually say it means that under the current conditions, you'll make buckets of product. And so delta G is tightly linked to the equilibrium constant. So if delta G naught is thermodynamically favorable, it's a negative number, and we would expect K to be much greater than 1, because much greater than 1 means that overall I have way more products than I have reactants at equilibrium. Now, delta G naught being unfavorable, thermodynamically unfavorable. It's kind of tough, I guess. I'm sorry about that. Okay, it's positive. K would be much less than 1, and that's because overall you're not making much products under those conditions. So thermodynamically favorable is saying that under that temperature and possibly pressure, I don't have any enthalpy or entropy barriers that cannot be overcome at that temperature. That doesn't mean those are both always favorable. It just means that if one of them is unfavorable, under the conditions we're measuring or discussing, in this case, standard conditions, that unfavorability can be overcome in terms of the delta H and delta S. So let's take a look at the math formula. So if delta G naught is equal to minus RT ln of K, I think it's good to learn how to estimate with natural logs. If K is much greater than 1, okay, then the ln of K is positive. So negative times RT times a positive number is going to be a negative number. So that gives you a little bit of an estimating ability instead of just a memorizing ability. So if we look at it the other way, if we have delta G naught is equal to minus RT ln of K, if ln of K is less than 1, if K is less than 1, then ln of K is negative, so I'd have delta G naught is a negative times a positive R times T times a negative, so delta G would be a positive value. So that shows you kind of conceptually what the links are. Now let's plug and chug into this formula. K, in this case, for a solubility product, is much less than 1. So if K is much less than 1, we predict that delta G naught is positive, or it is thermodynamically unfavorable. So we have FeOH2. Always a solubility product is for the solid, going to aqueous ions. Make sure you write your cation and your anion, and then balance. And we're looking for the K value for this. Now, you want to watch units here. Delta G naught must be in joules. And we're going to always, when we're talking about energy, use R as 8.31 or 8.314 joules per mole Kelvin, and T has to be in Kelvin. That you've got to watch in thermodynamics. I would say units and signs are the big things that'll trip you up. So we want to find delta G naught. Okay, and so delta G naught is going to be minus 8.314 times the temperature, which is 298. In AP chemistry, it's assumed to be 298 unless you're told otherwise. So that's at 298 times the natural log of 1.6 times 10 to the minus 14th. And once you plug that in, you get 7.9 times 10 to the fourth, okay, joules per mole of reaction, which if you put that into kilojoules, it should be 79 kilojoules per mole of reaction. Okay, now just as a reminder, if I wanted to do further calculations, I'm going to form 1 mole of iron 2 plus for every 1 mole of reaction. And I'm going to form 2 moles of hydroxide for every 1 mole of reaction. So if you ever had to get that mole of reaction to cancel, those are the coefficients, those are the conversion factors, that you would use. Okay, now there are other times with free energy, and I'm going to apply Hess's law and K, in which a favorable reaction can drive an unfavorable reaction. So we say that these reactions are coupled, happening at the same time, so that the thermodynamically favorable reaction can drive the thermodynamically unfavorable reaction. So if we added these two reactions together, we would get a total free energy of minus 17.6 kilojoules per mole of reaction. And it asked me to calculate the equilibrium constant for this. So if we coupled the reaction, we would add these together and those would cancel. So I'd get ATP plus glucose yields ADP plus the glucose 6-phosphate. I'm just going to shorthand that there. Okay? And so we want to find out what K is for this, but bear in mind you have to have joules. So this has to be converted to joules before you can plug that in. So we get minus 17,600 is equal to minus 8.314 times 298 times the natural log of K. And we need to do some mathematics here. The negatives would cancel. And the opposite operation of natural log is E. So if I take E to the 17,600, look at the function keys. So if you look at the keys on your calculator, the opposite operations are typically the same key. One is just a function key. Okay, 8.314 times 298 in the denominator. Watch your parentheses there. And that would equal our K. And I got 1.22 times 10 to the third. Well, hopefully that is a logical number. K is much greater than 1. So we proceed to make lots of products. In other words, it is product favored, which makes sense since we have a thermodynamically favorable delta G. So hopefully this gives you a good idea of how to use that equation. And I'm going to do one more shorter video in which we will link these to Q, non-equilibrium or non-standard state conditions. And so until then, this is wishing you lots of learning as you study chemistry.